Hey guys, welcome back. So now let's proceed with the next topic. So in this video we'll be looking upon two main topics, and the first one is how Ohm's law fail in certain condition, the limitations of Ohm's law, and the second one we'll be looking at is the temperature dependence of resistivity. So these two topics. So let's now start with the first one, which is where and when Ohm's law fails. So I'll just write on the heading. Okay, so we know Ohm's law that states that the potential is directly proportional to the amount of current flowing through it, and when you equate it, it becomes V is equal to I times R, where R is the resistance. So this proportionality, that voltage is proportional to current passing through it, is not always true, and this statement can be broken in three main cases. So there's three cases, and the first one is that V is not proportional to I at all times. This is one of the cases when the potential is not always proportional to the amount of current flowing through it. This is one case where it fails. And then the second case is when the potential, when you change its magnitude, that is, let's say the positive side of the battery is connected to left end of a device and the negative side to the right end. You have a certain amount of current flowing. But now if you reverse the polarity, the same amount of current might not flow. It's not a guarantee that it won't flow, but there is a chance that in most of the cases it won't be the same amount of current. When you reverse the polarity, the current changes, and that is a violation. If the voltage has been made negative and the magnitude is kept same must apply to current, but that's not what we observe. So that's the second case. So this is the second point, that reversing the polarity of the voltage, which means changing the sign from positive to negative or negative to positive, does not always give correspondingly expected current. So this is the second point. And now the third case is when two different voltages may be given by the same amount of current. You can understand this with a graph. When the same current I in a graph, let's say this is the graph, this is the voltage and this is the current. The same current I, let's say here 5 amperes, could give two different voltages at two different times. Like the graph could be in this form. So here you can clearly see that there is one voltage and two voltage correctly at this given current, and this is the third case. So these are the three cases how Ohm's law fails. These are the limitations of Ohm's law. So, but even though it's not obeying Ohm's law, it doesn't mean these devices are of no use. In fact, these devices are the ones which are mostly used in electronic circuits. So next we'll look at the temperature dependence of resistivity. So I'll erase this off. Okay, so temperature dependence of resistivity, as from the name itself we know that resistivity of a material is a constant only at that temperature. As you defer the temperature, it's also going to change in magnitude. So there is a quantitative way of knowing how much the resistivity will be at a different temperature, and it is given by this equation. Resistivity at a temperature T to the ratio of resistivity originally at another temperature is equal to 1 plus alpha into difference in the temperature of this T and initial conditions. Temperature difference. Or else you can also represent the bracket as delta T, which means difference. So you can rearrange it and write it as temperature at any temperature T is how much resistance was there initially, resistivity sorry, into 1 plus alpha times delta T. Delta T is the change in temperature between these two conditions. Here alpha, so this is the equation to find the resistivity at any temperature T. And here alpha is called the temperature coefficient of resistivity. If you notice, this is very similar to the ones you learned about expansion of metals, and this was linear expansion coefficient. It's very similar to that format. This is temperature coefficient of resistivity. Now this is the only mathematical equation, and this is how all you have to know. But now let's see how changing the temperature will affect resistivity in three different material types. So you can note this down if you want. So I'm going to use the three different material types. First is metals, then I'm going to use alloys, and then you're going to use semiconductors. Okay, so these are the three types. Now let's look at the graphs of these three, of resistivity versus temperature. So you have resistivity in the y-axis and temperature. That means as you increase the temperature, we'll see what happens. So resistivity of metals is going to increase in an exponential way when you increase the temperature. So it's going to start from 0. Let's assume it starts from 0 and then it just goes in an exponentially increasing way. For alloys, it still increases, but it's not an exponential increase, it's just a linear growth. It starts from a certain value and it increases in a straight line. This is for alloys. The examples of these could be brass, and examples of metal here is copper. Here I'm writing nichrome. And semiconductors is the different one. Semiconductors, it's just the opposite of this. It decreases its resistivity as temperature increases. As temperature increases, the resistivity decreases in an exponential way. So if you see, these become less and less have conducting properties. As you increase the temperature, the resistivity increases, or in other words, they become less of a conductor and more of insulating properties. Whereas it's the opposite in semiconductors. So we saw this, how they behave, but let's see why. Let's see why metals show increase in resistivity as you increase the temperature. Resistivity, when we say, generally it means the resistance to the flow of ions. So let's see how. So here I'm going to make use of the formula we just derived in the previous video, that is formula for resistivity in terms of relaxation time tau. So I'm going to write resistivity equals m divided by n e square tau. So if you see, m is a constant and e, which is charge of electron, is a constant. So the resistivity of any material depends only on 1 by n tau, where n is the number of free electrons and tau is the relaxation time, which means the average time interval between two collisions. First you have an electron, let's say, and another electron collide. Now this has zero velocity. The amount of time it takes for this to regain to the original drift velocity and collide again with another, that amount of time interval is known as the relaxation time. So what happens when you increase the temperature? You're going to increase the velocity, you're going to increase the energy of the electrons. That means it's going to, let's say this is again the same electron, now with a higher temperature. So as soon as it gets collided, it's going to lose energy, same as previous case. But now, since temperature is higher, it can regain its kinetic energy much faster. That means it can again collide much faster, which means that the average time interval, or tau, decreases. As temperature increases, tau or time decreases. That means the denominator has decreased, which leads to an increase in resistivity. And this is exactly the case of metals. When you increase the temperature, you are increasing the kinetic energy, which causes to less amount of time between collisions, and thus the reciprocal resistivity is higher. But how is it the opposite case in semiconductors? Well, in the chapter of semiconductors you will learn. So here we will just say that you have to look at the net effect of this product. In case if n was more in increasing, like let's say if that n has a better property of increasing than how much the time can decrease, the product is overall going to increase. So that means tau is again going to increase. So in semiconductors, what happens when you give more energy is that more number of electrons, more number of ions are made free to move. They escape from their energy gap and they can jump to the next energy level. That means you have created more number of electrons or any ions. So n increases in this case. For semiconductors only, for semiconductors, temperature increase implies N increases. So when N increases, the reciprocal resistivity decreases, and this is what we saw in the graph. So this is all about temperature dependence of resistivity. So in the next video, we'll go to the next part of the chapter, which is electrical energy, power and work. After that, we can look at the properties of resistance, and we'll be introducing to different types of rules to solve for resistances easily. We have learnt about series and parallel circuits, but in more complex junctions, it will become complicated. So over there, we'll be using a law known as Kirchhoff's law. After that, we can solve them easily. So I'll see you all in the next video. Thank you for watching. Subscribe and stay tuned.